Hello everyone. My name is Harshil Kothari. I am a third-year graduate student at University of Toledo, and today I'll be presenting Probing the Heights and Depths of White Dwarf Atmosphere, a case study of Y0359. So before I show some exciting results, I would like to remind everyone about the uh, spectral coverage that we had pre-James Webb. So before James Webb was launched, space-based spectroscopic data was limited for white dwarf to Hubble, which covered a wavelength range of from roughly 1 to 1.7 microns. We had some ground-based M-band data, which covered a wavelength range of roughly 4.5 to 5.5 microns, and we also had some photometric observations from WISE and Spitzer, which covered a wavelength range of 3 to 5 microns. And now, this is what we can get with Webb. So this is a spectrum in F lambda space of 0359, which is a white dwarf from Byler et al. 2023. We use this spectrum to do a cloudless retrieval using the Brewster retrieval framework, which was set up for 19 dimensions. So I'll break down the dimensions for you. 9 of the parameters were mixing ratios. 3 of the 19 parameters were physical parameters, which were mass, radius, and distance. 2 of them are nuisance parameters, which dealt with the wavelength uncertainty and error inflation. And the rest of the 5 parameters were used to generate the temperature pressure profile, which was a phi naught spline. Sorry. So here is a zoomed in version of the previous corner plot, which shows all the mixing ratios. So the first 9 parameters are the mixing ratios. And at the end over here are the mass and the radius. So, I should also mention, we also retrieved for phosphine and we didn't detect any. So sorry about that. Using the mixing ratios, we also calculated the atmospheric C2O, which is approximately 0.55. We also calculated the surface gravity, which in log is roughly 4.45 centimeter per second square. We also calculated the effective temperature, which is roughly 460 Kelvin. So you might be wondering how much better are our retrieved abundances using the Webb spectrum. And so here is a plot that shows or compares our retrieved mixing ratios to the previous work, which was done by Zaleski et al. In 2019. So Zaleski et al. In 2019 did a comprehensive retrieval analysis of white dwarfs, which included the retrieved mixing ratios for water, methane, carbon monoxide, carbon dioxide, and ammonia. And so in gray here are the posterior distributions of those mixing ratios. And in red are the mixing ratios that we retrieved using the Webb spectrum. And you can see that they are better than what we could previously do. With the I should mention the gray distributions were retrieved using the Hubble spectrum. And so this shows like how much better we can do with Webb. Also, you might notice that there are no distributions here for CO and CO2, and that's because the Hubble didn't cover the absorption bands of carbon monoxide and carbon dioxide. So here is a plot that shows how our retrieved model compares to the observed spectrum. So in the top panel, in black is the observed spectrum, in green is the retrieved. Kelvin on the vertical axis is the log of the pressure in bars. So as you go up, the pressure decreases. The next curve here is the retreat median profile, and the red regions show 1 and 2 sigma credible interval.
Harshil,
And-
can I swap you?
That's what.
Yeah, you can swap that because they can't hear you online.
Okay. Let's stop swapping. Okay. So you might notice that the temperature pressure profile is not very well constrained. In fact, the median 1 sigma credible interval in this profile is roughly 200 Kelvin. And so the reason that it's not very well constrained is because Hubble probes from roughly one to 1 to 100 bars in pressure levels, and that probing is denoted here in this these gray Gaussian-looking curves, which are also known as contribution functions. So they show you the part of the atmosphere that a Hubble spectrum is probing, and so you will notice that as the temperature pressure profile goes outside these pressure levels, the uncertainties of the profile increases, and that's because the Hubble spectrum does not probe those pressure levels. So now you might ask, how much better can Webb do? And the answer is literally 10 times better. So on the right here is the retrieved temperature pressure profile from the Webb spectrum. And so in the black is the median profile, and the red regions show 1 and 2 sigma credible interval. In this profile here, the median 1 sigma interval is roughly 20 Kelvin. And the reason that it's so precisely constrained is because Webb probes at least an order of magnitude more compared to the Hubble spectrum, as you can see here from the contribution functions. So the next thing after we did, after we got the retreat temperature pressure profile, was we compared it to the forward model. So here in the first panel, the black curve is the median profile from the previous plot. And in green here is the forward model temperature pressure profile, which is the ELF-R forward model. That has an effective temperature and surface gravity that is effectively the same as our object. And you can see that it does not fit that well. So if we start from here, which is from 0.01 bar, and go down to up to 10 bars, you'll see that our retreat temperature pressure profile is systematically hotter than the forward model. Once you go below 10 bars, our retreat profile is systematically colder compared to the forward model profile by up to 500 Kelvin. And so this shows that more work needs to be done to improve the forward model profiles. Using our retreat temperature pressure profile, we calculated the chemical equilibrium profiles of the major gases, which are water, methane, ammonia, carbon monoxide, and carbon dioxide. So here is a plot where on the horizontal axis is the log of the volume mixing ratios, whereas you go to the right, the value increases. On the vertical axis is the pressure in bars, so as you go higher up, the pressure decreases. And you can see the profiles, for example, for water, it's uniform for a while and then it condenses out at lower pressures. Methane is mostly uniform throughout the atmosphere. Ammonia first increases and then becomes uniform and then condenses out at lower pressures. CO and CO2 just its abundances just keep decreasing as you go higher up in the pressure. And the reason for that is the carbon chemistry favors methane, and an opposite thing is true for ammonia, where the nitrogen favors ammonia. So now you might wonder, how does our retreat volume mixing ratios compare to the chemical equilibrium predictions? And so here, the solid bars show the retreat chemical profiles. And so, for water and methane, they are very close to the prediction. But for CO and CO2, they're very different. The retreat values are higher compared to the chemical equilibrium predictions. And the opposite is true for ammonia, where its volume mixing ratio is lower compared to the chemical equilibrium prediction. So why is that? And the reason, so this basically shows that not all gases are in chemical equilibrium, which suggests that this equilibrium chemistry is at play, and so there is vertical mixing within the atmosphere. Now, you can quantify this vertical mixing by something known as vertical eddy diffusion, which is often expressed as KZZ in literature. So one of our collaborators, Sagnik Mukherjee, calculated that KZZ value for us by running a chemical kinetic model using photochem to generate a grid of chemical forward models using our retrieved chemical profiles to calculate the KZZ in the atmosphere. So the way that works is you vary the metallicity, the atmospheric C2O ratio, and KZZ values until you find a fit for the chemical profiles. In this case, it was our retrieved chemical profiles, and this is the value that we got, 10 to the power 9. So we can plot our value onto this figure here on the top, which is from Miles et al. 2020. So it's a plot that shows KZZ versus effective temperature. So on the horizontal axis, you have the effective temperature. On the vertical axis are the KZZ values, and the solid circles here are models with the different surface gravities, and these dashed curves at the top are theoretical upper limits for KZZ values. And if we place our value on the plot, it's basically pretty high up. So it's in the upper limits, and which tells us that there is strong vertical mixing in the atmosphere for our object. And so this brings me to the last part of my talk. So Sam Byler mentioned earlier, we have 24 objects within our sample, which consist of T6 two Y1s. And so I ran cloudless retrieval for all of those objects and calculated effective temperature and surface gravity. So in this plot, on the horizontal axis is the effective temperature in Kelvin, on the vertical axis is log of gravity. As you go higher up, the gravity increases. These gray curves are evolutionary tracks. And so now there are two things to notice here. The first one is just look at how all the objects follow the evolutionary track. It's just insane. And the second thing is our assumption that brown dwarfs roughly have an age of 1 to 10 gigayears can be seen here. Most of our objects fall within that range, and so our assumption is pretty good. And so with that, I come to the conclusion that the wide wavelength range of JWST spectrum helps tightly constrain the temperature pressure profile. There is a significant difference between the retrieved and the forward model temperature pressure profile. And with such precise constraints on the mixing ratios, we can calculate and constrain the atmospheric mixing rigor, which is the KZZ. Thank you. That's it.
So in this session, we've seen kind of two approaches to the data, right? Taking kind of high resolution but shorter wavelength range data versus what you've shown, where you have this really broad wavelength coverage and get fairly more constrained temperature profiles than with the shorter wavelength data. To do these retrievals, should we always be getting kind of a full XED?
Short answer is yes. But no, it really depends on the science that you're trying to do. Our goal here is to we want to calculate the effective temperatures. If you want to calculate the bolometric luminosities, then yes, you need to go to, you need a wide wavelength range. But if you are trying to really probe like specific absorption features over certain wavelength, then, you need a high resolution data. But with high res, you cannot go like wide wavelength range. Or maybe you can, but if you can convince the tech, but I guess not. So it really depends on the science you're trying to achieve. Yes. If calculating the C2O ratio and metallicity is the goal, then wide wavelength range is the way to go. Yes.
So, did that amazing results. So thank you. I wonder, like, can we use data to improve the model? Like, how should we improve the alkaline metallurgy? Like, can you have you tried how small or how bigger the alkaline opacity should be to better fit your data? So that models can better improve their data.
I think we can do that. I have not tried doing that, so I don't know.
Really, there's also, in a sense, contribution function of the abundances. And we're not really, we have these vertical abundances which then are dividing some of the conclusions. How far are we from being able to use a 5-knot slide for abundances and see these kind of, the contours like we showed for the temperature for the uncertainty of the vertical distribution of all the events.
I don't think I understand your question. Can you elaborate a bit?
I got this plot, right?
Yeah.
With the temperature.
Yeah.
But in principle, you can do the same thing for the molecular abundances.
Yes.
Right? You could have a 5-knot line for 5 species would have 25 more parameters, right?
Mhm.
Before AI replaces all of them.
Yes.
Is this something that you could do in the foreseeable future to kind of also understand where do we really know where the abundance is?
In theory, we should be able to do it now. It's all about computational resources. This takes a long time. For example, we did a 7-knot temperature pressure profile, and like it's just 2 more parameters, and yet it takes significantly more amount of time compared to the 5-knot profile. And so, and as you said, like we are increasing the parameters in your case, and it could just take an infinite amount of time to converge, and so it might not be feasible to do it yet. That answers your question?
Okay, let's thank Harshil one more time. I just have 2 quick announcements. Number 1, you may have noticed that everyone that just spoke, plus who's speaking in the next portion, is all